received okay, we'll do one thing, time being. So this ionosphere layer, I'll show it like this. This is the surface of the Earth. Transmitting, and this is a receiving station, or anything you can put it, receiving end. Receiver, I'll write it. It can be some tower or some mobile or some radio station, anything it can be. Don't say mobile, it can be some any receiving radio station, radio set. Now, what about the sky ionosphere? So what is the height at which it will extend? So it will extend from 60 kilometers to 60 to 350, roughly around 350. So to what height this particular layer, it will be from 60 to 350 kilometers for the ionosphere layer will be present here. This layer will have the C, D, E, F1 and F2. Again, this ionosphere is broken up into the layers like this. For the layers, what happen, I'll give the name. The layers, I'll give the name, that one. So I'm going to use that one. So how it is possible? And this is EM wave, no? So shall we go for the wave properties? So go back to the, this one, refraction at plane surface. And if a wave passes through a variable refractive index, what will happen to the wave? What will happen to the ray? The ray will bend. So for the ray, you just recollect and now I'll send the wave. For it to bend, what is needed? No, go back to the optics. There's a ray, I'm sending it here. Now it should bend away from normal. So what should be the requirement? The requirement should be such that it should move from denser to rarer. It'll bend like this. So then it will bend like this. Then if it undergoes here inside, say like some TIR, okay, there's an ionosphere. Inside the ionosphere layer, this is what happens here. And the different layers will have different refractive index. So you can write it mu1, mu2. Okay, fine. So the bending property of light, so like when a ray moves from one medium to another medium, due to change in refractive index, the ray can propagate like this. And this EM wave is nothing but, even the EM wave, just now we have concluded earlier chapter, like it will exhibit the refraction, reflection, diffraction, interference, all properties. From where the variable refractance will come, the ionosphere layers, the different layers will have different densities. From where the different densities will come, how that ionosphere, when the sun rays pass through that particular layer, the gases there get ionized. And it is mostly made up of the electrons. and the density of electrons will determine what should be the refractive index of the different layers here. I think if you refer some our integrated book, they're given all the densities. If you want to just have a look here, the different layers will have the different density. Because of different density, they are going to have different refractive index. I'll just write only equation. The refractive index, and n will use symbol. We'll use symbol n, because mu, what happened, we go for permeability, all that particular thing. So this should be equal to epsilon naught mu naught omega is the frequency of the incoming wave. N is electron density. M is mass of electron. And what about omega? Omega is frequency of reflected wave or frequency of incident wave. Incident EM wave. Okay, I agree with this. So there's a formula, or you can go for binomial expansion and you can make it little bit very simple. 1 by 2, or just keep it like this. Huh? So there's a refractive index, Ri of layers. The different layers, they will have different electron density. And because of that, the refractive index will be different here. And as the ray is projected towards it, it's going to bend it. So there's one major property of this particular thing. And if you look at this N naught, what is N naught? What is N naught? N naught should be equal to refractive index N naught, that one. And this first, what happened, this N dash will be less than N naught. Refractive index of ionosphere will be less than the refractive index of free space here. So what is N naught? What we should call Ri of free space. So from where I brought it, you can go back to the velocity of a ray of light in any medium, V equal to C by mu refractive index. I think, can you remember these formulas? What is mu? Mu is a refractive index, better say like a N. Then according to what is the speed of EM wave in any medium? I think you're going to write like this, no? Mu into epsilon. So shall we put refractive index, this formula? And for a transparent, for a glass medium, mu will be mu naught epsilon R into epsilon naught. Like this, the refractive index you can correlate. I'll write it in order, because again, this will help you a lot in some EM waves. They may ask you to calculate the refractive index of a medium. So we know that speed of a light in any medium is given by this formula. Then speed of light in any medium is given by mu epsilon. For the glass, mu will be mu naught. This will be epsilon R, epsilon naught. So mu naught, epsilon naught, epsilon R. So what you can write, root of 1 by mu. So this should be equal to C is 1 by root, no? So this will become C. So like this, the refractive index will be related to the permittivity of medium by this particular formula. For glass, it will be, for most of the glasses, mu naught will be 1. Non-magnetic medium, no? It will be mu naught will be, so mu R will be 1. Material or medium. Okay, I agree this. So let's come to our Ri of layers. Okay, this is a thing. So what can be this distance? This can go up to several thousand kilometers. Very large range. Okay, this one. So when I'm launching it, I can even launch in such a way Mhm. Okay, now, if I just change the launching angle, mean the same incident wave only, I'll just see that let it be launched in different angles. So as I launch it in using different angles, so the reception area will increase, not like only one user. So we can go for multiple users here. So here the same signal will be launched like this. Okay, look at the views here. So the different views. So this will be, so the reception area will be very larger. So this area, if you go for practically, it may cover up to South India, total South India it can come. So this itself will go for 1,000 kilometers. Reception area, we'll call it. Reception region. The reception region itself. So one-to-one transmitting station will go for that one. I think the British broadcasting station will agree this. I think it called like a Ceylon station we call, no? That one. So they're being in Europe, what pen from Britain, what pen they used to transmit the radio signals throughout the world. How they were able to use the ionosphere layer, and this distance is how much this will be put around 300 kilometers. So the BBC earlier the information what pen we used to have using BBC the total world. Just you have to listen to radio, you have to get the information of the total world. Till I think 1990. Anything what happened America, Europe through BBC only we used to come. So what they should do? So the transmit BBC station which is there in the London or some particular thing there. So they used to just send the same signals at a different angles. The same signals at different angles. Then open the reception area, it used to come like this, very large, 1,000 kilometers. Line of sight, not like that. Only few 10 kilometers or 30, 40. Ground wave propagation not like that. So this is the advantage of this one. That's why for British broadcasting for earlier, no, the radio communication they used to use. Even now the DTH, we use the same method. Back to ohm, no, we use the same method. Okay, getting the idea, no? So this is about the basic ionosphere propagation. What is the biggest problem? Is like, what is the range? How do they reflect? What are the conditions? So first, what will happen? For any frequencies, it can send the waves. So the answer is no. So let me go for one more. There's a surface of the earth. Now, what are the range of frequencies that this particular communication mode will set up, will supply? So if I send a let me send a I'm just giving explanation. So this will be the, if it is less than 2 megas, it will be absorbed, the frequency of this 2 megas. So what about this array 1? What about ray 2? Ray 2 is what? The greater than 40 megas. And what about this frequency? Lies between 40 megas to put 3 megas. We don't have exact boundary. If the frequency of the wave which is incident at ionosphere, if it is greater than 40 megas, what happens? They will penetrate through it. And with less than 2 megas will be absorbed. So the ray 1, this will be absorbed. This is absorbed. They will penetrate. and this will be reflected. Okay, there's a range of frequencies. All frequencies will not support, no, only those frequencies which will be between 3 megas to 40 megas will be supported by the ionosphere propagation, that one. So what that ionosphere layer, shall I say, it will just act like a reflector, nothing to do. It will bend the rays. So what is the duty of ionosphere? So what it does? It bends the rays. So first, and if you see that one, like that, if I keep on send, so what is the biggest problem is like the first skip distance will go for it. I think I'll give one more diagram. I think how much it can bend, I think there's some limit, no, it cannot bend very much. So here, I need one more diagram. So if I transmit the rays, so there is some bending will limit will come, no? So if I send like this, like this, I can keep on. So the further bending not possible. So this particular thing will become skip distance. So where the reception area is this one, receiving area. So what do you mean by skip distance? So it is a distance from the transmitter to a point where the ionosphere reflected waves will not be received. I think there's a simplest definition, or the diagram itself will speak here. The smallest distance from a transmitter. So we'll define the terms now. The smallest distance from transmitter measured along the Earth's surface to the point of measured along the point of surface where the sky waves returns to the Earth's surface. Okay, we'll define like this. This is smallest distance. So less than this, skip distance. The skip itself says that no reception of the signals here. So this will be of order how much? 52. So this will be from 50 to around it. It can come even 100 kilometers. So what to do? I'll go for ground wave propagation. I'll put one more transmitter using ground wave. I'll cover this particular thing. But this is something receiving area. It can go up to several thousand kilometers. That's what advantage. The 50 kilometer which I missed it, I'll cover by ground wave propagation. Okay, the skip distance. Coverage can be done by ground wave propagation. Okay, there's a note. So that I can cover everything from transmitter to the last till receiving end. So there's the one first term we have introduced. So next again, I'll bring critical frequency. A small definitions are there. We'll finish off that one. The highest frequency of radio wave which when sent normally towards the given layer these are definitions, possibility of asking, that's why I'm just trying to put it in order. Gets reflected from ionosphere. So this depends on what? 9 into the electron density, the maximum electron density. So if the frequency is less than this, what will happen? Highest frequency. If it is greater than this, what will not be reflected. Less than this, S will be reflected. So shall we say critical is that highest frequency of the radio wave when sent straight normally towards the given layer of ionosphere gets reflected from ionosphere and returns to the earth. This one. So next, maximum usable frequency. Last one more term. MUF, that one. Highest frequency of radio wave which when sent at an angle at a certain angle at I think, yeah, certain angle towards the given layer. Towards the given layer that gets reflected and returns to the earth. Okay, no. So this what? What is the meaning of this? So this, how do we express? This is given by MUF equal to FC by cos theta. What is theta? It is the angle between the normal and the incident ray, where at that given layer. So again, this diagrams are not there. You'll find very difficult to what is the meaning of this, and I just give small help. So this is the surface of the earth, ionosphere. So this is the normal, we'll take it. So here is what I'm going to send a ray. And gets reflected. So this is the angle of incidence theta. So then critical, this mu of the what is the critical frequency for this layer? I know it. At what angle theta it is incident, I'll come from cos theta. I know at what height this layer is located. Okay, clear this one? I know what height. From that, what happen? I'll calculate the range. Are you getting no? These are the types of numericals what you have in the book. Find the range if that particular angle of incidence. Where is theta? Theta is not launching angle. Theta is not launching angle here. Theta is the angle at which the ray is incident at a given layer. So you pick up this particular layer, hit a height, and you have to pick up which layer you are picking up. There, what happens? You should know what is the critical frequency of this. So then you have to ask questions. So why you are saying that you have to choose a layer? The critical frequency depends on what? Depends on electron density, and the electron density depends on what? Time. Because during night, there won't be like if you're using that layer during daytime, there'll be sunlight, and the electron density will change. During night, the electron density will change. So the given layer, what happen, will not have same density at all time. Even the density of that given layer will vary with the time. So based on that time, what will happen? We are going to pick up a layer. Suppose this having one density, the same density after 3 hours the same layer will not have same density after some 3 hours. So therefore what happens, we have to pick up a layers for different intervals of time during daytime. Usually what happens, we'll break up this for every 2 hours. If you see the radio transmission, what we do know, for every 2 hours, what happens, the time slot will be made and that particular layers will be picked up, because I want, say like a critical frequency or usable. This is very important. So which layer you are going to pick up and at what angle you are making that to incident, that will determine this maximum usable frequency. And the different layers will have different density at different instants of time, at different height at different instants of time. So during night, one layer will be picked up. During daytime, again, the same layer will not be picked up. Some other layer will be picked up here. And this height matters. Greater the height, what happens? The range will increase. So like that, based on the application tool where it has to be transmitted, no, the height we are going to choose. And what frequency I should pick up, and at what angle the ray will go and incident on that layer. That also matters a lot here. Because here, when it is bending, this is what, that theta. Because this theta is not launching again. I don't know, some books they're given theta here. Totally concept wrong it will become. With respect to, so this will be the boundary, no, and this will become normal. The angle made by the incident at a given layer with the normal with respect to given layer will become theta. So that will determine maximum usable frequency. Critical frequency depends upon the layer, which layer you are picking up at that instant of time. Able to understand? I think now, if you know H, if you know theta, can you bring the range? I think from the geometry. So what we can write, tan theta equal to d by 2 by h or d by 2h. So this theta again, you can calculate from here. So what frequency you are going to pick up, which layer you picked up, you'll get the theta. The theta will come here. Actually, the theta is in our control. Don't think that MUF, that one. The launching angle is very different. So you should orient your antenna in such a way that theta should come that much here. So therefore, this frequency I'll pick up based on this particular thing. What is the D? D will become no range. At what distance the rays will go and strike here. So there's a reflected wave. There's the incident wave. There's the ionosphere. I think just it's like a story, nothing big for you. Huh? Okay, you can, in NCERT book, there are no diagrams. Yes, given expression, there are no much diagrams. I think if you look at the integrated book, okay, there are some sufficient here and there some good diagrams are there. Of all, this is very important. Not one receiver. Whatever the receiving area, this will go to up to several thousand kilometers and thousands of receivers will be there. So what I do at the transmitting station, I'm going to have the incident wave only. I'm going to transmit a different orientation so that I can have a large reception area. There's a key idea of this one.